All right, so I finished my general announcements. Highlights our winter break packet was due the previous class. So students have today and the next class day to turn that in for 10% off. The 6.1 take-home quiz and 6.1 textbook work are due today. So students have 2 class days to turn that in for only 10% off. Okay, students were already given time on part A on 6.27. And again, this is a great, just very quick summary of the punchlines from yesterday, which basically comes down to we're trying to learn how to combine normal models. And when you are combining normal models, you are absolutely allowed to just straightforwardly add or subtract the expected values. However, with standard deviations, you cannot add or subtract them. You can only combine variances. And as you're about to see in a moment, you would never, ever, 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 ever subtract variances. This is not an intuitive thing, which is why on the next page, I will try to show a simplistic example to try to point out why that is the case. Okay. So jumping out on the next one, it says difference in weight between a German Shepherd and a Siamese cat. So if you want to know the expected difference, no problem. Go ahead and subtract the mean values. Expected German Shepherd minus expected Siamese cat. Boom, you get an expected difference of 48 pounds. So in context, this is again under the assumption that you're you is if I randomly select a German Shepherd and randomly select a Siamese cat and weigh them both, in general, I'm expecting the German Shepherd to weigh about 48 pounds more than the cat. Okay. Now, there's going to be fluctuation in that. The problem is what a lot of people want to do is they want to basically repeat the calculation they did in part A, but with a subtraction symbol in between. This would be wrong. One of the rules that I want you to learn today, and again, I'll try to break this down with a more simplistic example on the next page, is that variances always add. So the weird thing is you would do the exact same thing you did in part A. Literally the same thing. It doesn't matter if you're adding normal models or subtracting normal models. Variances always add. That is a rule. Okay. So the model that describes the expected difference, while it has a very different center value of 48 pounds, A and B have the exact same standard deviation. This can be an uncomfortable thing to be exposed to. Okay, but we'll dig into that in a moment. Now, the next two problems are very similar to problems that we saw yesterday in concept. Okay, I'll try to remind people. Yesterday, I proposed this game where you roll a die, and if you roll a 1, 2, or 3, you get nothing. If you roll a 4 or 5, you get 5 points, and if you roll a 6, you get 25 points. Now, one of the questions was, what would a normal model be for playing the game one time and just doubling the number of points you get? Whereas another question that we talked about yesterday was, what would a normal model be for playing the game once and then playing it again and adding your points together? And intuitively, it may feel like that's the same thing. Like, what does it matter if I play it once and double my points versus playing it twice and adding my points? Isn't 2x the same as x plus x? And the fact of the matter is, no, it's not. When you're combining normal models, if you're just going to do 2x, you have one source of variation. You roll the die. That's your only source of variation, because once you're done, you just double whatever you got. Doubling it is not a source of variation. It's a scalar change. Whereas if you play it twice, well, you don't know what's going to happen on the first roll. That's one source of variation. And you don't know what's going to happen on the second roll. That's a separate source of variation. So now you're in a situation where you don't just double the standard deviation, you have to have double the variance. And mathematically, it ends up with different numbers. Okay? So that's kind of what's happening here. In C, it says weight of a typical German Shepherd in ounces. And it reminds you there's 16 ounces to a pound. Now, you already have the model for a single German Shepherd. That was given in the problem. If you want to convert this to ounces, that is a scalar change. You have one dog, one source of variation, and all you're doing is taking the weight of that one dog and scaling it up so it's in out of ounces. So this would be the model for one dog in ounces. However, if the question said total weight of German Shepherds, 16 German Shepherds, that's no longer a scalar. It would make, and let's be clear why this is very different. It would make absolutely no sense to do the same thing we did before. Here's the only way this would make sense. If you were guaranteed all 16 German Shepherds will weigh the exact same amount. If you were told that, if this was like, what's the total weight of 16 identical clones of German Shepherds, then fine. The moment you know one, which is variable, you don't really know what that one's going to be, you instantly know what all the other ones are. They don't provide additional opportunities for variance. It's just one German Shepherd that's copied 16 times. Fine, call that a scalar change. However, in this case, you have this German Shepherd plus this one, plus this one, plus this one, plus this one, plus this one. Now, no problem. Go ahead and add all of their expected values. I expect this one to be 59.5. I expect that one to be 59.5. I expect this one to be 59.5. Fine. Go ahead and multiply that by 16 because adding it 16 times is the same thing. However, for standard deviation, what you have to realize is that every single dog provides its own variance of 6.5 squared. And you're combining 16 sources of variation. So this is what you would have to do. You have to say one dog has a variation or variance of 6.5 squared. And I'm combining 16 copies of this variance to get the total variance of all 16 independent dogs. And then I take the square root of that mess, and I end up with a very different number than what we had in problem C. Okay? So to be clear, notice that C and D have the same mean, but they have very different standard deviations. Okay? And by the way, the opposite happened with A and B. A and B had different means because one was talking about adding and one was talking about subtracting, and yet they both had the same standard deviation because standard deviation will always add. Okay, so each problem on this page has a kind of a purpose, and there are two sets of problems that are meant to teach you a lesson. A and B is variance is always add. C and D is there's a big difference between a scalar of 16 and 16 independent sources of variation. Questions? All right, so the next page, the top half has a point, the bottom half has a point. Okay, the top half, I'm hoping this will be an example that helps it click for you all. It's my way of trying to show you why variances will always add. Okay, if you have one thing that's uncertain and you have another thing that's uncertain, meaning two things that are variable, I don't care if you're looking at the sum of them or if you're looking at the difference between the two. In either case, you are increasing your level of uncertainty in the system. Okay, so variances always add. That's the point of the top half. The bottom half is another example to just try to prove to you all the mathematics that we're using to combine normal models literally literally require that the separate models be independent. Okay, and if they're not, the mathematics we're using in 6.2 kind of break down. Okay, if the models you're trying to combine are in some way related to each other or connected in some way, the mathematics we're using don't actually apply anymore. Okay, so let's start with the top half. This example involves range, not variance, for simplicity. However, both are measures of spread and thus behave similarly. So imagine a pitcher and a cup of lemonade. Now, you don't actually know how much is in either one. The pitcher has somewhere between 20 and 26 ounces. The cup has somewhere between 4 and 6 ounces. Now, can anyone volunteer? We're going to fill in 3 blanks here for how much lemonade might be in the total. Can anyone volunteer what is the minimum amount of lemonade that would have to be in total between the pitcher and the cup? 24 ounces. Okay, if the pitcher has the minimum 20 and the cup has the minimum 4, you have a total of 24 ounces. Can somebody else volunteer the maximum that could exist in this system? I heard 32, because maybe the pitcher has 26 and the cup has 6, and if they both have their maximum, well, then you have a total of 32. Now notice the range in the complete system is 32 to 24. That's a range of 8. And notice the original range of the pitcher was 6, the original range of the cup was 2, and lo and behold, 6 plus 2 is equal to 8. Now again, I'm not talking about variances right now, I'm just trying to show you a simplistic example, but ranges and variances are both measures of spread, so they kind of behave in the same way. Okay, so here's the summary so far. If you have 2 separate sources of variation and you add them, the variations also add. The ranges add. Okay, the spread adds. Now, what if I give you the exact same numbers in every way, but I change the context so you're subtracting the 2 ranges instead of adding them? So now imagine the glass is empty to start. The pitcher still is 20 to 26. So you don't know how much is in the pitcher, but it's the same 20 to 26 ounces. You're now going to subtract from the pitcher. but you don't know how much you're subtracting. You pick up the pitcher, you pour some into the cup. You don't actually know how much you poured in. It's somewhere between 4 and 6 ounces. Notice it's the same numbers that were presented before, but now we're subtracting 2. Now, I still want volunteers. I'll warn you, this one's a little funkier. Can anyone name for me the minimum amount that might be left in the pitcher given this scenario? 14. The way you get 14 is you started with the minimum amount in the pitcher, that's 20, but you poured out the maximum amount 6. Does that make sense? So the minimum you could possibly end up with in the pitcher is 14 ounces. Now, can somebody else volunteer what would be the maximum amount that might be left in the pitcher? I appreciate it, but I'm hoping to hear from somebody new. Somebody said it? Where'd it come from? Kevin? All right. So we've got maximum is back here. Okay. Hold on, give me 1 second here. I knew it. Sorry, Eric. My apologies. All right. So the maximum is 22. We've got 26 minus 4, which is 22. Okay. Now, what is the spread between 14 and 22? What's that spread? 8. Notice it's the exact same spread. Okay. So before, when you had 2 sources of unknown variation, okay, and you were adding the 2 sources, you ended up with a total spread of possibly 8. But when you had those exact same numerical ranges and you were subtracting an unknown amount from an unknown amount, you still ended up with the ranges adding to be a total range of 8 in what you might end up with. So what I'm trying to show you with this example is, I don't care if you are adding sources of variation or subtracting sources of variation, the level of uncertainty that now exists in the system in either case has gone up. Does that make sense? So again, the punchline is, when you are combining normal models, you will always add variances. Okay. Now, mathematically, the only thing I could think of where, yes, fine, you might have to subtract variances is if I paint a picture where you're solving backwards. Like, just back up for a moment. If I told you this model, okay, or yeah, that was the one that was subtracting. So if I gave you this model and I gave you one of these, then fine, you might have to use those 2 values. You might have to use this number and this number to work backwards to figure out that one. But to me, that's not really a counterexample. That's just doing a certain process where you're always supposed to add backwards so you can solve for one of the initial values. Fine. That would be a situation where you need to subtract variances. But that's why I said, when you are combining normal models, always add variances. Okay. Now, the other really important condition, okay, is that the models have to be independent. So that's why I designed this one, to try to give you an example of why that's such a big requirement. Okay. So let's review one condition assumption all these calculations rely on. Only independent models may be combined. See what happens if not. Okay. So we're going to let X represent the hours you're asleep in a 24-hour period. Now, if I asked you all how many hours you slept last night, I don't know what kind of numbers you were going to get me. So we're just going to assume the average is hopefully around 7 hours, not much lower. Okay. So we're going to assume for a moment 7 hours is the average amount of sleep with a standard deviation of 2 hours. Okay. Remember, what that means is 68% of you got somewhere between 5 and 9. 95% of you got between 3 and 11. And pretty much everyone always should have been somewhere between 1 and 13. Okay, hopefully you're not below 1, and more power to you if you're above 13. Okay. In any case, if we wanted to find a normal model for X plus Y, our predictions, our procedure would say to do the following. Okay. You would add the expected values, 7 plus 17. I have no problem with that. You would add variances. So you take 2 squared and 2 squared, which is 8. You take the square root of that to get the standard deviation. So our process would say, if this is the average amount of sleep with a standard deviation of 2, and this is therefore the average amount of awake, again with a standard deviation of 2, well, then this is the model that describes the sum of the 2. But here's why that makes absolutely no sense. Okay. How much sleep did you get last night? How much sleep did you get last night? All right, 7.5 hours. I instantly know that she was awake for 16 and a half hours in the last 24-hour period. How much sleep did you get? 5 hours. I instantly know he was awake for 19 hours. Okay. The moment I know how much you were asleep in the last 24 hours, I instantly know how long you were awake for the last 24 hours. And by the way, if I asked all of you right now, picture in your head how many hours of sleep you got. Get that number in your head right now. Got your number? Now, how many hours were you therefore awake? Everybody get those numbers. So you should have one number. Okay, for me, what was that number? I went to bed kind of stupid last night. I went to bed at pretty late at midnight. I got up around 5, so I got 5 hours of sleep. I know I was awake for 19. So my numbers are 5 and 19. Now, if your number was 5, your other number is 19. If your number was 7.5, your other number is 16.5. Everybody got your numbers? Now, what I'm suggesting is your sleep numbers all vary. So 7 hours average standard deviation 2. Your awake hours all vary. I'm assuming an average of 17 with a standard deviation of 2. However, if I asked all of you right now, add your numbers together. Everybody do that now. Take your sleep number, take your awake number, add them together. You got, notice how everybody's saying 24? Okay. If all of you were following me in this, then when you added your two numbers, you should have gotten 24. Everybody got 24, 24, 24, 24, 24. So the model that describes the sum of awake and asleep, even though awake varies, even though sleep varies, when you add them together, you should always get the number 24. So the true model is actually 24, 0, because there's no spread. It's just 24, 24, 24, 24, 24. So our mathematics, which says the model that describes the sum of the two is this, makes absolutely no sense because there's no spread. It's just 24, 24, 24, 24. The reason our mathematics breaks down is because clearly there's a link between how long you're awake and how long you're asleep. Does that make sense? They are not independent. They're clearly dependent. And so you can't use the processes we're learning right now. Questions? All right, turn the page. All right. So 6.29 says SAT scores for the Clarksburg High School class of 2013 were. So this is back, by the way, when there were 3 sections to the SAT. I know that only existed for a short period of time, and I know currently it's now back to only 2 sections, but back then it was 3 sections: reading, math, and writing. Even if these models are representative of the next class of Clarksburg High School students, why would it be inappropriate to construct a normal model for composite total score? Okay, so let's pretend for a moment, and this is a ton of green stuff, that it was appropriate. You don't need to write anything down right now because everything I'm showing you is something you shouldn't do. You can't do because the question says, why would it be inappropriate to do this? However, if you could combine these and you were asked for a probability a randomly selected student would earn a composite score of at least 1700, here's what you'd have to do. You'd have to add all the expected values to get the total combined expected value. You would have to add the variances, which means you take each standard deviation, square it to convert it to variance, add those variances, take the square root to get the standard deviation. You now have a normal model that allows you to say, okay, I expect you to be around 1498, but how weird would 1700 be? Okay, like how often, according to these models, would a randomly selected student get at least to 1700? So you go to your z-score calculation and say, all right, well, how weird is 1700 when I thought you get 1498 and a standard amount of spread from 1498 is apparently 173. And lo and behold, this is a z-score of about 1.165. So then we jump to our graphing calculator and we say, all right, normal CDF from that marker up, and you end up with about 12.2%. So if you were allowed to add these models, then I might ask you a question like that. How often would you expect an individual student to get at least a 1700? Boom, there you go. However, we can't do that. Anyone tell me why? Because they're not independent. Now, if you just wanted to say scores for each section are likely to be dependent, no problem. The fact that you say scores and section, that's your context. But if you wanted to dig deeper into what does that even mean? Like, what does it mean for them to be dependent? Here's an example of what you might say. Because a student that scores above average in one category is probably more likely to do so in other categories. Okay. If I find one student that got a reading score of 400 and I find another student who got a reading score of 770, I'm not going to be shocked that the kid who got 770 also scored higher in math. Does that make sense? Like if you're really weak in one, well, then it stands to reason you probably are weak in somewhere else. But if you're like really, really strong in one, then you probably make sense that you're stronger in the others. Okay. I'm sure there are exceptions to that pattern, of course. There are plenty of people out there, I'm sure, that do exceptionally well in one category and completely do terribly in another. But in general, if you have a bunch of people that did really well on the reading and a bunch of people who did really poorly in the reading, I'm not going to be surprised that the group that did really well in reading in general did better in the other sections as well. Okay. There's definitely a link between the three. And because there's a dependent link, you can't do any of this. Questions? All right, I gave students 6 minutes to work ahead here. Again, the first thing I would do is create a model that represents the total expected time. So I would add each of the expected values. You get an expected time of 200.57 seconds. Okay. And then we get a standard deviation of 0.461 seconds. Something you had to realize is that this is a model based on seconds. So you need to convert the time of 3 minutes, 19.48 seconds to 199.48 seconds. So this is essentially what you're asking yourself. If in general their combined time is 200.57 seconds, how likely are they to get a combined time of less than 199.48? So basically, how unusual is 199.48 when you expected the total to be 200.57, and a typical amount of variation from that 200.57 is 0.461. And by the way, anybody who knows anything about swimming, especially at the Olympic level, variations of a half a second is a huge chunk of time. So, when you're talking about 4 people swimming 4 different events, and in general, them being within a half second of a certain time, that's actually not that strange. That's a pretty standard level of variation. Okay, even though it may sound really specific. So the area under that tail is very, very small, certainly less than 5%. So you could argue in terms of, it says, do you think the team is likely? You could argue, as far as I'm concerned, one of two things. You could point out, well, no, I don't think it's likely because the z-score means they are more than 2 standard deviations away from expected. Anything more than 2 standard deviations is what we consider an outlier. So I don't think it's likely. It would be unusual. Or you could point out that the probability is less than 5%. Okay. We've said before that if you that observing something that would occur less than 5% of the time by chance is an unusual occurrence. Questions? I would imagine I have something to reveal. Yep. Just adding a few notations to the picture. All right. So I gave students 6 minutes to work ahead of me on problem 6.210 that we already went through. I then gave students 5 more minutes to work on 6.11. So this is the model, and these are the values that you would have filled in to construct and label a normal model for the total expected bicycle setup time. Now, the next question says something about it being ready in a half an hour, in 30 minutes, and you're asked, would you consider this to be unusually fast? The quick way to answer this is to notice that 30 minutes is more than 2 standard deviations away. So yes, I would consider this unusually fast because it's more than 2 standard deviations away. You could also take the time to actually calculate the z-score and get the probability of that happening and point out that that probability is less than 5%. I don't actually care which avenue you'd rather attack with. Okay, but either one would be perfectly acceptable. Obviously, the blue is a bit faster. Okay? Questions? All right, we are done for the day. Thanks for watching. Have a good one.